Namaskar, welcome to the KTHM College Nasik and welcome back again to the lecture series of third year B.Sc course Astronomy and Astrophysics. So since from last few lectures we are talking about solar system, planets, celestial bodies, universe, stars and galaxies and etc. And we came to know about the astronomical units of distances. We have determined the diameter of any celestial bodies in the space. We have determined the distances between the planets or distance of planet to the sun or earth by using the parallax method. Then after that we have discussed about the planetary motion. We studied Kepler's 3 laws that earth and all the planets are rotating around the sun in elliptical orbit. With the help of Kepler's second law, we determine the velocity of the planet which are revolving in elliptical orbit around the sun. With the help of Kepler's third law, we estimate the mass of sun as well as the time period of revolution of all the planets which are revolving around the sun. So in this lecture, we are going to talk about the electromagnetic spectrum. The light is coming from the sun, or light is coming from stars, or light is coming from the source is full of electromagnetic spectrum. As we already discussed about electromagnetic spectrum in 11th or 12th standard. Then after that, the very important and very interesting, the Wiens displacement law. And we will end this lecture with the Doppler effect. So electromagnetic spectrum is the range of all types of radiations having different wavelength and different frequencies. Radiations is nothing but the energy that can travel and spread out all over. All the radiations containing in electromagnetic spectrum travels at the speed of light no matter what their frequencies or wavelengths are. So we can read the electromagnetic spectrum with their different frequencies and different wavelength. So light is an electromagnetic wave, and when light is coming from the source, it is full of electromagnetic spectrum with their different frequencies and different wavelength. So we can draw the electromagnetic spectrum associated with their increasing order frequency or decreasing wavelength. Make sure that this arrow indicates the increasing order. So first wave, radio wave, it is the longest wavelength of radiations or lowest frequency. Then after that, microwave, then IR, infrared radiations. Then everybody knows visible spectrum. We know the visible spectrum with increasing wavelength or increasing frequency, red color, having longest wavelength. So it is in the left side. And Vibgyor. Then UV, ultraviolet radiations, X-rays, and the gamma rays having lowest frequency or lowest wavelength or highest frequency or highest energy. Because we know the relation between energy that travels and spread out is nothing but the radiations. Okay, and I already discussed about the wave particle dual nature. Wave behave like a particle and particle also behave like a wave. So waves, radiations are waves, and the particle nature of the radiations are nothing but photons. So E is equal to h nu, where h is the Planck's constant Nu is the frequency of that radiation. That is nothing but energy. Or we can write energy is equal to hc by lambda. Or we can write nu is equal to c by lambda. So frequency is inversely proportional to wavelength. If radio wave has longest wavelength, so it has low frequency or lowest energy radiations, while the gamma ray having highest frequency or highest energy, it has lowest frequency. So we can draw the wavelength nature of the electromagnetic spectrum. So it is having, the wavelength goes on decreasing. Something like that. So wavelength is nothing but the distance between two crests, lambda. I hope it is clear. As we know that our universe is the clusters of stars and galaxies, and sun is our closest star. The light is coming from the sun, and we know that sun is too much hotter and bigger than earth. So can we estimate, or can we measure the temperature of sun? How does it possible to measure the temperature of sun by just simply sitting on the earth? Then the Wiens gives a big breakthrough for the astronomy. We can just simply sitting from the earth, we can measure the temperature of sun or stars or any galaxies in the universe by using Wiens displacement law. So to understand the Wiens displacement law, we must to know about the black body radiation. So black body is the physical body that can absorb all the electromagnetic radiations incident on it. Or we can say that it is the surface that absorbs all the radiant energy falling on it. And hence the visible radiations will be absorbed then reflected, and the surface will appear black. But it does not mean that the black body always appear black. The black body is the ideal absorber that absorbs all the electromagnetic radiations, but also it emits electromagnetic radiation when hot enough. So at room temperature, black body appears black. But if we heated it enough, then it will become a good emitter also. So at room temperature, black body emits IR radiations which are invisible for our eyes. But the temperature of the black body is near about 900 degree Kelvin, then it will become visible for us. So the point is that if black body absorbs all the radiations and it is a perfect absorber, then it is also perfect emitter of light when hot enough. So for that we have to understand the black body radiation curve. If we consider a black body and if we heat it up to temperature 900 degree Kelvin, then it would start emit radiations. So the number of radiations are emitted per unit area per unit time is nothing but the intensity of that radiations. So if we plot the graph of intensity of radiations, so intensity means the number of radiations or the number of radiations having total energy. So the energy per unit area per unit time is nothing but the intensity. So if we plot the graph of intensity versus wavelength of that radiations, so we'll observe the black body radiation curve. So here wavelength and intensity, or we can say that the energy, the total amount of radiations emitted from the black body when we heated it per unit area per unit time is nothing but the intensity. So if we plot the intensity versus wavelength or wavelength versus intensity graph, so black body nature at temperature T, let's say T is the temperature when we hit the black body enough, then the nature at temperature T1, let's say T1. So at this point, the radiations having particular wavelength, or at this particular wavelength, the number of radiations are emitted are this much, something like that, here only. But at this particular wavelength, the number of radiations are more, or large amount of radiations are emitted. So the large amount of radiations of these particular wavelengths are emitted, which is having maximum intensity. So the radiations having maximum intensity occurs at particular wavelength is known as lambda max. It does not mean that lambda max is nothing but the maximum wavelength. It is the wavelength having, or it is the radiations having this much wavelength, or the radiations having this wavelength are in large quantity per unit area, per unit time. When we hit it, the black body, it emits the radiations. I hope it is clear. So this is the lambda max. It observed that when we increase the temperature of that black body then the maximum intensity peak is shifted. The lambda max, I repeat, the lambda max is not the maximum wavelength, whereas the lambda max is, it is the wavelength of that radiations which are in large quantity by the emittance of the electromagnetic radiations by the black body per unit area, per unit time. So the lambda max is shifted towards the lowest wavelength, because wavelength is increasing in this case, and lambda max is shift towards the shorter wavelength, right? As temperature increases again, the lambda max shift towards the shortest wavelength. So this is the black body radiation curve nature. This is the ideal nature of the black body. When we hit the black body, the amount of radiations are having particular wavelength is lambda max, and if we increase the temperature of that black body, then the lambda max is shift towards the shorter wavelength, or we can say that the lambda max is displaced towards the shorter wavelength. Hence it is called as Wiens displacement law. So in this case we can say that the Wiens displacement law is nothing but T is directly inversely proportional to lambda max, right? So as temperature increases, lambda max decreases. Okay, it is moving, or it is shifted or displaced towards the shorter wavelength. So we can write the proportionality constant T is equal to B upon lambda max, where B is constant, and it is also known as Wiens constant. So that Wiens constant B is nothing but 2.898 into 10 raised to minus 3 meter Kelvin. Therefore, we can write it here from this equation, B is equal to T into lambda max. So if T1 is the temperature that given to the black body radiations, and black body radiations emit radiations. So at this T1, the lambda max is here, and if you take the product of T1 and the lambda max, so you will get the constant B, which is nearly equal to this. If you take T2, the product of T2 and the lambda 2 max here, then we will get the product which is nearly equal to this. It means that T1 lambda 1 max is equal to T2 lambda 2 max equal to T3 lambda 3 max and so on. So hence this product is constant. This is the Wiens displacement law, and which is equal to 2.898 into 10 raised to minus 3 meter Kelvin, which is constant for all. So one interesting thing is observed that the radiations of maximum intensity of the electromagnetic spectrum occurs from the sun is at 500 nanometer. So the lambda max, when we take the spectrum, electromagnetic spectrum of sun, or the light is coming from the sun, or light is emitted from the sun acts as a black body. When it emits the radiations, and if we take the spectrum of that radiations, so we observe that the lambda max, or the maximum radiation intensity, occurs from the spectrum of sun is 500 nanometer. And then if you put the value in Wiens displacement law of that lambda max, so which is nothing but so the temperature of the sun, which is equal to 2.989 into 10 raised to minus 3 upon 500 nanometer. And here we can do the simple calculations. 2.989 into 10 raised to minus 3 upon 500 into 10 raised to minus 9 meter. So minus 9 at numerator. So we will have, the answer is I think 5967. You can do the calculations by using calci. Degree Kelvin. So this is the temperature of the sun. Similarly, we can estimate the temperature of any stars and galaxies by just simply sitting from the earth with the help of Wiens displacement law, because we know the Wiens constant, and if we take the electromagnetic spectrum from the sun, from any star or from any galaxy, and if we are able to find out the lambda max of that electromagnetic spectrum which are coming from any stars or galaxy, so we can estimate the temperature of that stars or galaxy. I hope it is clear. We can observe the Wiens displacement law. If we hit the iron rod at 900 degree Kelvin, then it would start emit radiations, and at 900 degree Kelvin the iron rod emits the radiations and it will become a red deep or longest wavelength. Further increase the temperature of that iron rod, it changes colors to the red, from red to orange, and then orange to yellow, and finally the blue at very high temperature near about 10,000 degree Kelvin. Now let's talk about the Doppler effect. Let me ask you a question. Why sky looks like reddish in the evening or in the morning, and why it looks like a blue in the afternoon? So you'll understand this concept by studying the Doppler effect. We already discussed about Doppler effect in the last year. So Doppler effect in light. Our universe is expanding continuously. I told you in the first lecture that the Big Bang theory predicts that the universe is continuously expanding, and all the celestial bodies in the universe are running away and apart from each other. So how we can conclude, or how we can predict that all the planets, all the celestial bodies in the universe is running away from each other with the help of Doppler effect. So Doppler effect is nothing but the apparent change in frequency due to the relative motion of the observer and the source. So if we consider the source here, source of light, and the observer is stationary. So the case is that if source is moving towards stationary observer, we know that this is the source and which is moving with velocity. Let's see, cs is the velocity, and the light which is also moving with the speed of light, right? We know that frequency nu, or let's say n, is the frequency. So relation is nothing but n is equal to c by lambda, where c is the speed of light. But the case is that this is in case of when both are at stationary. When the source and observer both are stationary, then n is the frequency of that light which is moving towards the observer, which is having velocity c and wavelength lambda. But in case of if source is moving towards the stationary observer, so source also have certain velocity and which is denoted by cs. So due to the relative velocity, because we know that if car A and car B both are moving along the same direction, then the relative velocity Vr is nothing but Va minus Vb. But if car B is moving in opposite direction, then the relative velocity Vr is equal to Va plus Vb. Make it clear. So in this case, the velocity of source as well as velocity of light both are moving in the same direction towards the stationary observer. So therefore their relative velocity is, I can write here, so the apparent change in frequency, or we can say that apparent change in lambda, which is equal to lambda prime, which is the apparent change in wavelength, which is equal to lambda prime is equal to c by n, where c plus, now both are moving, not c plus, both are moving in the same direction. So the relative velocity is nothing but c minus cs upon n. So this is the apparent change in wavelength. Therefore the Doppler effect saying that the apparent change in frequency, which is equal to c by lambda prime. So therefore n prime is equal to c. What is lambda prime? We can put the lambda prime here, c minus cs upon n, c minus cs upon n. So n prime we can write c upon c minus cs into n. So if this value is 1, it means that n prime is equal to n. But in case c minus cs, this denominator is small as compared to numerator. Therefore this value is greater. So n prime is greater than n. So the apparent change in frequency is greater than the natural frequency, or the frequency when the both are stationary, original frequency. This is the apparent change in frequency. So apparent change in frequency is greater than the natural frequency. It means that the source is moving towards the stationary observer. And the case second is that if source is moving away from the observer, so in this case apparent change in frequency is more, right? So it means that wavelength is, apparent change in wavelength is less. So in second case, when source is moving away from the observer, stationary observer, so therefore we can write lambda prime is nothing but c plus cs, because source and velocity of light, the direction of light is towards the observer, but source is moving away from the observer, so therefore relative velocity is c plus cs upon n. So therefore n prime is nothing but c upon c plus cs upon n. Finally n prime is nothing but n into c upon c plus cs. So in this case, denominator term is more than numerator, so this value is less. So therefore n prime is less than n. So the apparent change in frequency is less than the natural frequency or the original frequency. It means that the source is moving away from the. So from these two cases, we can observe that if the apparent, when the source is moving towards the observer, then the apparent change in frequency is more. And we can say that lambda is, if frequency is more, lambda is minimum. If frequency is maximum or frequency is increasing, lambda is decreasing. And in this case, apparent change in frequency is less, so lambda is more, because both are inversely proportional to each other. So in this case, source is moving towards the observer, lambda is less. So blue color has shorter wavelength, lowest wavelength, right? So in this case, the source is moving away from the observer, then the apparent change in frequency is less and the wavelength is more, and hence sky looks like reddish, having highest wavelength when it is in vertical position, when it is in horizontal position. So in 1923, Edwin Hubble observed that the electromagnetic spectrum from the stars and galaxy, and he superimposed that electromagnetic spectrum on the electromagnetic spectrum which is observed in the laboratory. And when the electromagnetic spectrum from that stars or galaxies, he superimposed on the stationary electromagnetic spectrum which is obtained by the stationary source, and he observed that the electromagnetic spectrum is shifted towards the red end of the electromagnetic spectrum, and hence he concluded that the universe is expanding. So I hope it is clear, and you are very well familiar about the Wiens displacement law and the Doppler effect. So we'll finish this model and we'll start the next model from the next lecture. Thank you very much.